All right, on that note card I gave you, I want you to draw a hexagon. You can use a straight edge like your ID, or there's rulers in there if it helps. Just make it as regular of a hexagon as you can. And you can make it big, like take up most of the note card so that you could write this on the outside of it, okay? Whichever one. It doesn't really matter because it's really the only thing you're putting on there. So if the lines like help you draw it, that's great. If you would rather it be on the solid side, that's fine too. So you're going to draw it, and you're going to draw the actual diagonal lines in there as well. So let's just have a little bit of geometry view. This is a hexagon. It's a regular hexagon. Yours may not be regular, but mine wouldn't either if I drew it by hand. But we're going to pretend, right? If it's a regular hexagon, what does that mean? It has 6 sides. That's what makes it a hexagon. What makes it a regular hexagon? All sides are congruent and all angles are congruent. Okay, good. And so then when you draw in these diagonals that you are drawing in, you get 6 triangles. What's true about them? They're all congruent. And what kind of triangles are they? Equilateral. And only because it's a hexagon, not in every polygon. Okay. It's okay. Just draw it the best that you can. And you know what? We'll get through this. Don't even stress out about making it great. This is what I'm going to do. We're going to draw on this thing. I didn't even have, I wasn't going to have you do this. And then Ms. Rice was like, I had my kids do it on a note card too. And I was like, well, okay, well, let's do that. So I'm going to give you another note card. So for right now, I just want you to draw it on the note card. And even if it's like weird and bad and then it's going to drive you crazy, you're going to have another note card that you can go and do a beautiful hexagon on it if it's bothering you, okay? And then later on, if you feel like having this note card would be helpful to you, you can redo it, and there's an extra note card. And if you feel like maybe you don't need the note card, you can just have the notes sheet that I'm going to give you. That's fine too. But that way we don't spend an hour trying to make the most beautiful hexagon in the world, okay? We'll just get it as good as you can, and then you have an extra card that you can take with you and do with what you want. Yes, draw the diagonals and the 1. And then as you build this, because here's the idea, and here's why I want you to actually draw it and why I think that's a good idea, is that when you're trying to use it and understand how this is going to help you with identities, you got to make sure that you're actually writing these things in the right places, okay? So you start with sine and cosine on the top 2, okay? And then the middle is tangent and cotangent. And then if you notice along the diagonals, like tangent along this diagonal, okay, tangent along this diagonal here gets you to cotangent. Sine, the diagonal gets you to cosecant. Cosine to secant. So how are cosine and secant related? They're what? Reciprocals. So the diagonals connect the reciprocals, okay? And that's really and then so that order matters. If you get sine and cosine in the right place, sine, cosine, and tangent in the right place, and then there are reciprocals across from them, and then you have that 1 in there, and you have this magic hexagon, okay? So then on your hexagon, and I'll have you do this on your paper as well once you get this from me, is I want you to highlight, I'm trying to figure out how I could, this triangle here, the one that has sine and cosine on the vertices. Highlight it, or like you can shade it in with a marker. I didn't necessarily mean highlight. And then every other triangle. So when you build it, even if you're building it in your head, like maybe you wouldn't draw it every time you ever need it, but when you're trying to picture it in your head, you get sine and cosine and tangent in the right spots, and then the reciprocals across from them. this triangle with sine and cosine, and one is colored in, and then it's every other one. Okay? So I'm going to give you a green notes sheet that has that same hexagon at the top, and go ahead and shade in those triangles just like you did on there, and then we're going to look at it. Actually, before I give you that, I'm going to talk you through some things, and then we'll talk you through it again. So here's what this says, because I'm afraid you're just going to be reading this and not paying attention to me. This gives you your identities. So it gives you the quotient identities or your ratio identities. Quotient and ratio, same identities. Tangent of theta can be written as a ratio of what? Okay, yes, it can be 1 over cotangent, but it can also be what? Sine over cosine. So look, tangent is sine over cosine. See how that works? Cotangent is what? Cosine over sine. Well, if tangent is sine over cosine, the reciprocal of sine is cosecant, so that flips it to the bottom, right? And cosine is secant, so it flips it to the top. So tangent is also the reciprocal of secant over cosecant. Cotangent is the reciprocal of cosecant over secant. Not the reciprocal, I'm sorry. Cotangent is the ratio of cosecant over secant. Does that make sense to you? And then secant is it's not the reciprocal. Secant is the ratio of tangent over sine. No matter which way you go. Grab this one, tangent is the ratio of secant over cosecant. Secant equals cosecant over cotangent, and you just go all the way around it like that, in any direction. Okay? The only two that you really have on your basic identities is that tangent is sine over cosine, then you can really get everything else from that, just moving them around. And cotangent is cosine over sine. But again, I know that cosine is the ratio of cotangent over cosecant. Okay? Does that make sense? So that's just the quotients. There's more. Okay? Then there's the product identities. Right? So tangent is sine over cosine, right? So if I multiply tangent times cosine, what do I get? Sine. Because look, here, I'll write it out and then I'm going to erase this. I know that tangent is sine over cosine, right? You agree with that? So if I multiply this times cosine, I'm left with sine, right? So if I multiply tangent times cosine, like I multiply both sides by cosine, that means I'm going to get sine. So tangent times cosine is sine. Multiply these two together, you get the one in between. Okay? So what is tangent times cosecant? Secant. Tangent times cosecant is secant. What is cosine times cosecant? Cotangent. What's sine times cosecant? Sine times cosecant, 1, right? Tangent times cotangent, 1. So you bring them in together and you get that right there. Sine times cotangent gives you cosine. And the little paper I'm going to give you explains all that. I wanted to talk you through it before you're just reading all that. So it reminds you of that so you can kind of look at it and think about it a little bit more. Yes, sir? You can multiply across the diagonal like sine to cosine, but I can't multiply well actually yeah, you can multiply in any of them. If I multiply tangent and cosine, that brings me together at sine. Or tangent and the one across from it gives me 1. Okay, does that make sense? And there's examples on here too. We'll look at it again after I give it to you. All right, so then the reciprocal identities, which is what I told you is how we really build it anyway. Sine is 1 over cosecant. Cosine is 1 over secant, tangent is 1 over cotangent, and they work that way too. Then there's the Pythagorean identities, which this is where you might want to draw little arrows on your card for Pythagorean. I know that sine squared plus cosine squared equals what? 1. Okay? And then starting in the top left corner of the triangle again, 1 plus cotangent squared equals cosecant squared. Does that make sense to you? And then tangent squared plus 1 squared is secant squared. If you go back around from the arrow, 1 minus cosine squared equals sine squared, right? Secant squared minus 1 equals tangent squared. Secant squared minus tangent squared equals 1. Okay, so you kind of play with it. Okay, so it might be one of those things where you kind of get the gist of it now, and if you look at this and you think about it when you're doing it, and you kind of learn how to think around the hexagon, this can really help you with these. Because past the proof, like we did identities and we just simplified some. We're going to look at proofs today, and then we are going to use these same ideas and these identities to be able to solve equations. Okay, so it's important that you kind of know them and understand them. And then we have something called cofunction identities, which we actually didn't talk about as far as identities are concerned, but remember that sine and cosine, I can make the graphs look the same, it's just a shift, right? And so they're called cofunctions because I can make cosine look like sine and sine look like cosine, and it's just a shift from the parent function of how much? What's the shift to get me from a cosine to a sine graph? Pi halves, right? Pi halves or 90 degrees, same thing either way, right? So sine is the same as cosine of pi halves minus x. Tangent is the same as cotangent of pi halves minus x. And then secant is the same as cosecant of pi halves minus x. They're their cofunctions that are straight across from them like that, okay? So do you think once you kind of understand this more, and I put this in front of you, that thinking through this might be something that can kind of help you keep things straight? So let me give you this, and go ahead and so the card I thought might be a little bit more handy than always the notes. And again, you can make a better one, or maybe I can just make you better hexagons. Would you rather me just make you better hexagons on little cards? I think you drawing it out's good. You've got an extra card if you don't like the way your hexagon looks. And then you can obsess over it later. I know how it is. It would bug me too. I'm not even a perfectionist, but I know my hexagon would not look good, and then it would drive me nuts. So we'll talk through this again so you can understand the notes. I've got little examples on each part for you. And this I want glued in your ISN, and I don't remember what page I told you, 123? Yeah. This is going on 123. So here's the big magic hexagon. So here's where it explains the quotient identities and follow around the clock in either direction. So it's showing you tangent is sine over cosine. And then they're all listed here, but basically you start anywhere and go in any direction, and you get the quotient or the ratio identities. Okay, everybody good on that one? So then on the inside, the product identities, and this is showing you how you can just multiply from from two vertices that are non-adjacent to meet that are non-consecutive to meet in here, and then you can multiply across to get those. Okay, because these are the reciprocal ones. And so there's some more examples. They obviously aren't all listed out because there's a ton of them. But if you can picture in your mind, you just like close your eyes and see that hexagon and think about the order of them. Basically, if you memorize what the hexagon looks like, your identities are there. Okay, does that make sense? You good? All right, and then reciprocal identities. Okay, you go through the one, and that's again how you build it, which would be, I think reciprocals we got down. So if you know those and you can build the hexagon, you can get to everything else you need. Then the Pythagorean identities. Okay, so it shows the arrows there, and then the different ways that you can look through them. Okay. We're all good with those? Helpful? And then cofunctions, which are important for you to know, and it works because, like, if I know that the sine of 30 degrees is going to be the same as the cosine of 60, tangent of 80 the same as cotangent of 10, and so forth. Okay, we good? That's why I know you probably have wondered. We have tangent and cotangent. Those go together, it makes sense. But sine doesn't go with cosine. The reciprocal is cosecant. But it is a cofunction with cosine. So that's where the co comes in with the names. Right? We good on the magic hexagon? Okay, should be a little bit helpful to you maybe? Yes. All right, now we're going to look at proofs, or did you have any major questions on the identities? Remember, it's good to kind of struggle through them. Have you been working on them? A little bit, yes? They're puzzles. Do you feel accomplished when you get one that you've worked on a while? Yes, okay. Yes, and you're like, woohoo, look at me. Yes, and it's exciting. And I worked, the assignment that you have today, there were 2 on there that I worked and I reworked and I kept erasing and I was like, I'm going insane. But come to find out, they were typos. So when I give you the homework, make sure I tell you what the typo is so that it doesn't drive you insane, because I thought, oh my God, I can't even work these. How am I going to give them to them? Okay, apparently I can work them if they're typed right. That is the good news. All right, this is totally blank, I know. Just, now I got to find my... Fold it in half. I started to type things in there, but it really wasn't even necessary. But I wanted you to have at least something where you could organize stuff. Where is my... Here they are. All right. So this is going to go on page 1. Are we on 124 now? 124. And these are Trig identity proofs. All right, so proofs, these are very formal proofs. But the good news is you're not having to justify each step. You just have to do every single step. Okay? We did some proofs in geometry, not nearly as many as we did back in the day when I took geometry and was like all proofs. But this is more really like the algebraic proof, where when you work in a problem that's algebraic, if you skip some steps, as long as you show some process, it's fine. It's all good. But in a proof, you have to show every single painful step. And it seems absolutely ridiculous, but that's kind of part of a proof. So just like then, just be thankful you're not having to justify each step and that you just have to show each step, and it's all good. So we're going to start. Number 1 is going to look like this. I'm going to have 1 plus the tangent of theta over 1 plus cotangent theta. Now the difference between what we're doing today and what we've been doing is this is kind of what you've been given that you have to then simplify. But instead of trying to get this down to 1 term, I'm going to tell you that it is equal to sine theta over cosine theta. So your goal is to make one side look like the other. You do not have to start with one side. You don't like always have to start on the left or always have to start on the right. But think about this. Is it easier for you to take something like this and make it into a ratio that you can manipulate? Or is it easier to take something like this and try and figure out what type of ratio you're supposed to put it in? I mean, if you had to start with this to manipulate it to get to one side or the other, which side do you feel like you already know you could do more to? Well, the second side, what is sine theta over cosine theta? Tangent theta. Okay, that's a true statement. But that's not what I'm trying to make it look like. Because so then I'd have to figure out what could I like build in randomly to get tangent theta look like that. And there's so many things, I don't know that I'd want to go that way. But I can do some things here where it would give me stuff to work with where maybe I could get down to this spot. Okay, does that make sense to you? So you kind of have to decide. It's usually a pretty good decision. It's just which do you feel like you could do more to? Not which side is easier. It's really like which side is more complicated, because then you have things you can change. Okay, so we're going to take this, and I'm trying to get it into sine and cosine, so I'm thinking I probably need to make that tangent theta and cotangent theta into ratios of sine and cosine. Yes? So I'm going to, on the left, do 1 plus, well, instead of tangent theta, what am I going to do? Sine theta over cosine theta. Now, I'm going to also change something in the denominator. But even if I wasn't, I couldn't just keep working on the numerator and leave the denominator off and then throw it back in at the end. You have to rewrite the whole thing every time. Like whatever I have here has to be equal to the step that was right above it. So then I can do 1 plus, all right, so I can change cotangent to what? Okay, cosine theta over sine theta. Okay, and that's equal to, you don't have to rewrite this in every single step, but just know that it's basically we're going to bring it down at the end. All right, now, I have a fraction and a fraction. I could multiply by the reciprocal at this point, but I think that would be kind of yucky, like that really wouldn't work out too well here. Instead, I would like to get, instead of multiple things in the numerator and denominator, I would like to get a common denominator in the numerator and a common denominator in the denominator so that I could add these two pieces. Okay, is that going to be easy enough? What would I change 1 to in the numerator? Cosine over cosine. So this is going to be cosine theta over cosine theta plus sine theta over cosine theta. Now, even when you knew to get a common denominator, which was kind of an easy thing to do, you probably already know what it would look like as one fraction, but you don't get to skip that step. You have to change that, and then in the denominator, what's the 1 going to look like in the denominator? Sine over sine. Okay, so we'll have sine theta over sine theta equals, not equals, dang it, plus cosine theta over sine theta. Everybody with me? Okay, so now that I have that, I can actually combine those fractions in the numerator and denominator. So the numerator is now going to become cosine theta plus sine theta over what? Cosine theta all over, and then in the denominator, this numerator is sine theta plus cosine theta all over sine theta. Everybody with me so far? Okay. So now I have a fraction divided by a fraction. Is dividing fractions easy or difficult? It's easy, right? I think it's difficult, but it's not. You multiply by the reciprocal, so you got to be careful on these steps as well. This is cosine theta plus sine theta over cosine theta, and that's equal to sine theta, not equal, dang it, multiplied by times, because I'm multiplying, times sine theta over sine theta plus cosine theta. Everybody good so far? That looks kind of ugly, right? But what happens here? These cancel out, right? These two cancel out here. So when I multiply, I get sine theta over cosine theta. Now that equals tangent theta, but do I want to make it into that? No. Isn't that my goal? So at this point, I say that equals sine theta over cosine theta. Right? I'm going to put a little check mark because I showed that it works. And then I've got this basically brings down to here. If I can just do my arrow, I didn't have to rewrite it 1,000 times. Okay. Everybody okay with that? Oh, and I should have told you you could take up all of the front. I'm sorry. I meant to tell you that so you weren't trying to cram space. Which most of you probably did anyway, but if you were like trying to save space, I should have told you. We good? Any questions? So it's very similar to what you've been doing. You just know what your goal is this time. When you did the other ones, you didn't even know what your goal was, right? Your goal was one term, but you didn't know what it was. Now we know what it is. Yes? Okay. Questions? Okay. Let's go on, and we're going to do another one. Number 2. So this one is going to be so on the left-hand side, and this one doesn't take up nearly as much room, but we are going to use you can use the whole left side because the number 3 is going to take up all this space. So this is 1 minus cotangent to the 4th theta equals 2 cosecant squared theta minus cosecant to the 4th theta. So my suggestion would be that if you have anything that has a 2 in it, or any sort of coefficient that's not like just a 1 that's in there, I wouldn't start with that side because you're not really sure where that came from. Like something canceled out somewhere and you don't know what it is to be able to put it back in to make it look like the other side. And it's not that it's impossible, it's just there's too many options to make it doable. Which means I want to start with the left-hand side. So what could I do with the left-hand side? Any ideas? Okay, I can factor it, right? Is this an easy thing to factor? It's the difference of two squares, right? Okay, because I can take the square root of both of them. So if I do that, I'm going to get 1 minus cotangent what? Squared theta times 1 plus cotangent squared theta, and then put my little equal sign there. Now, let's go back to this. Look at your little note card. I don't have my note card, so I'm going to have to show you this. Okay. I know from here that 1 plus cotangent squared equals what? Cosecant squared, right? So I can change this one right here to cosecant squared, right? And what does just cotangent squared equal? Oh, I should have asked that differently. I'm sorry. It is cotangent squared is the reciprocal of tangent squared, yes. But cotangent squared is what? It is cosine over sine. But notice how, okay, that's good too. Let's talk about that. I don't want, I know I want my cosecants and stuff, so I'm thinking I don't really want to make it into sine and cosine just yet. I can, and it may get me where I need it, then I kind of get it back. But if I'm just want to replace, because I know that 1 plus cotangent squared, that is cosecant squared theta. We know that one, right? But the 1 minus, right? So I can't just replace it with one thing, but I can replace the cotangent squared theta, right? I can do 1 minus, and then if 1 plus cotangent squared theta, 1 plus cotangent squared theta equals cosecant squared theta, then what does cotangent squared theta equal? Cosecant squared minus 1, right? So I'm going to replace this with the cosecant squared minus 1. Does that make sense to you? Everybody with me on that? So this is minus cosecant squared theta minus 1. Did I write everything down correctly? This right here replaces the cotangent squared theta, right? If you are going to subtract more than one term, what do you have to make sure that you have? Parentheses. Otherwise, I'm going to get 1 minus 1, which is 0, and then I got nothing, right? But I have, these need to be parentheses right here, because I'm subtracting that whole thing, okay? So this is going to give me then 1, well, it's 1 minus a negative 1, which is what? 2. So that's actually 2 minus cosecant squared theta times cosecant squared theta. Everybody with me on that? And so notice that we know a lot of things about what cotangent could be and cosecant could be, but since I know my end goal, if I didn't know my end goal, I probably would have changed cotangent squared to cosine over sine 2. Yes, sir? 1 minus a negative 1. Okay. That's why those parentheses are so important, otherwise that doesn't work out. So now, what would I do now? Here's my goal. Can I distribute this? Cosecant squared theta times 2 gives me 2 cosecant squared theta minus what? Cosecant. What's cosecant squared times cosecant squared? Cosecant to the 4th theta. Then what do I need to do? Yeah, bring it down because I'm done. That's what I wanted. 2 cosecant squared theta minus cosecant to the 4th theta. Bam, right there. Okay, and that one was a whole lot shorter. Okay, we good? Any questions? All right. So the next one's a little yuckier. So we got, yes. What's the question? What? Okay, then what's your question? You might not be the only one. Nobody in here talks. I welcome questions. I believe you. No, come on. What is your question? Yeah, because he's not paying attention anyway because he's on his phone. But, so I tend to believe maybe he doesn't. He probably has a question like, "What the heck did you just do?" Because I wasn't paying attention. All right. So you got two options here. Tomorrow, you're just going to have time to work on these proofs, okay? Because I'm going to give you the work today. I want you to get started on it. You're going to just kind of work in class on them tomorrow. But I did tell you we're having a quiz today. We can take the quiz today and stop right here because it's good enough to get you started on the proofs. Or I can work the next example, which I think I've just changed my mind. I'm going to leave that second example until tomorrow, I think. I'm going to go ahead and give you that quiz because it said I'm going to let you use your little note card. Just the note card, not the notes. But you can have the note card in front of you. See if that helps you, okay? And then we're going to do the third example tomorrow. I'm going to give you the assignment right now, and I'm going to tell you where the adjustments need to be made. And then I'm going to give you the quiz. And then once you finish the quiz, you can work on the homework, okay? I think that's what I just made my own decision right in the middle of my little question for you.